Okay, 1.3 part 3. Explain why the function is guaranteed to have a 0 in the given interval. So 0 means x-intercept. So they are asking between 0 and 1, how do we guarantee it? So first you say f of x is a polynomial, so it's continuous everywhere. It's a polynomial, it's continuous everywhere. You say it's continuous. Then you plug it in 0 for x, plug it in 1 for x, get the function value. One is negative, one is positive. So we talked about it. Sign change, y value changes its sign from negative to positive, then means they have to pass between somewhere. So you say, therefore, by intermediate value theorem, we have at least one 0, at least one x-intercept between 0 and 1. So if you didn't quite follow what that meant, basically, we got plug it in 0 for x, we got value of y as -2. We plug it in 1 for x, we got value of y as 2. So basically, we got 0 minus 2 here, 1 and 2 here. We got 2 points. And we said it's a continuous. It has to be connected somehow. So even though I don't know the exact graph, you have to connect them somehow. So there gotta be x-intercept between 0 and 1. That's all they're saying. Okay, pause it. You try, please. So how do we guarantee that? You say it's a continuous because it's a polynomial. You say continuous. Plug x value is -3. Plug x value is 3. Show y value, one y value is minus, one y value is positive. Then you say by intermediate value theorem, there gotta be at least one 0 between these intervals. Done. Limits at infinity. Okay, limit of f of x as x approaches to infinity, as x approaches to minus infinity. So this is combination of two different limits. So limit of as x approaches to infinity, f of x. And well, let's start with the minus. The limit of as f of x as x approaches to infinity. So that's left-hand limit. That's a right. No, let's not use that. That's more like a limit to the point. So this is as you keep going to the left, as you move to the left. So left hand limit. And this will be right hand. Right hand. As you go to the right, as you go to the left. So x approaches to minus infinity as you move to the left. X approaches to infinity as you move to the right. So that's infinity. And that deals with end behavior of a function. And they are horizontal asymptotes of a function if there's a limit. So for example, equation like this. If you keep going to the right, keep going to the right, keep going to the right, y value is increasing, but it's approaching 2 to the over 2. Like if you keep going to the left, keep going to the left, y value is keep increasing here, but it's approaching 2 minus 2 over 2. And that's called end behavior. Right hand approaches certain value, left hand approaches certain value. So this case, you cannot write like this because this is a combination. So you will have to write to the left end, it will be minus 3 over 2. To right end, it will be 3 over 2. So that these values will be different. You cannot write like this altogether. Okay, use the graph of this to describe its end behavior. Okay, so if you have graphing available, you have dealt with this end behavior before. As you go to the left hand, very left, I meant, very left, keep going left, what happened to the y value? Decreasing. As you move to the left, y decreases. As you move to the right, what happened to the y value? Increases. Okay, so many of you have experience with dealing with writing like this. As you move to the left, as x approach to the left, as x go to the left, y, which is f of x, decreases. And you can say, as x approach to the right, as x move to the right, f of x increases. That's how we've been write the answer. Okay, as x approach to the left, fancy way of saying that is x approach to minus infinity right here. F of x decreases, that means y value is going to the minus infinity. So be very careful. This becomes this, okay? And increase, f of x increase becomes positive infinity. And that's a fancy way of saying x approach to the right. X approach to the right means as x approach to go infinity. Whether it's minus infinity means x go to the left, x approach to positive infinity, or x go to the right. Okay, this is a statement you should be able to write as ND behavior. Use the graph of this to describe its ND behavior. So as you go to the left, what is approaching to? It's actually approaching to 0. As you move to the right, what is approaching to? It's approaching to 0. So you might say, well, how am I supposed to know? It looks like keep going down. How am I supposed to know it's approaching 0 or it keeps going down? So for that, you might want to do some table. So if you plug it in very, very small number for x, you keep going to the left. Of course, x value is going to get a lot less than this, but just pick minus 10,000 for x value. Plug it in, minus 10,000, it's minus 0.001. That's almost a 0. Okay, your calculator might present the value as the following. E minus 4. It's a scientific notation. So minus 1, you start with minus 1, and decimal is here. E minus 4 means move decimal to the left. You go 1, 2, 3, 4 decimal here. So fill it up with a 0 here. Keep the minus. That's how you got minus 0.01. So if it was like 2, E3, that means start from 2, move E3 means move to the right by 3. Decimal 1, 2, 3. So you'll be 2000. That's how you deal with scientific notation. So if you keep going to the left, put x value very small number, it's almost 0. Going to the right, put x value very high number, like 10,000, it will be almost 0. So that's another way to confirm it will become 0. So left hand limit is 0, right hand limit is 0. That's how you say it. Again, be very careful how you say left, x approach to minus infinity. How do you say right, x approach to positive infinity? And both of them is approaching to 0. Okay, use the graph to describe its ND behavior. So keep going to the left, keep going to the right. So here's another confusion. Someone might say, well, it's keep going to the minus infinity, keep going to the positive infinity. It's not. So, well, how am I supposed to know? So you might want to do some table, plug it in very small x value, plug in very high x value. It's 0.6666. It's getting closer to certain value. It's not minus like 900, minus 900, minus 10,000. It's not going down. It's approaching the certain value, which is 2/3. Okay. Okay, so use the graph, describe the ND behavior. So same thing. It's approaching, keep going to the left, keep going to the left, keep going to the right. It's approaching to whatever this value is. So if you did some experiment with calculator, for a very small number, very high number, it's approaching to -4. So it's approaching to -4. Again, I don't particularly like this kind of notation, but I mean, I like to write separately limit of f of x as x approaches to -infinity, which is left -4. Then I like to write separately limit of f of x as x approaches to positive infinity, which is -4. So that's a left hand, that's a right hand. Okay, same question. So if you do table, I got -2 here, -2 here. So each approach to -2, each approach to -2. Okay, so using calculator, the ND behavior shouldn't be that bad. There's a shortcut you can do using rational function property. So I'm going to share that with you very quickly. If you get it, it will be easier. If you don't get it, you can still use your calculator. Just plug in the -10,000, 10,000, and all that. Okay, in the rational function, you have horizontal asymptote. There are three different scenarios. First scenario, if denominator has a higher power than numerator. I'm talking about the power of x. If denominator has a higher power than numerator, then y equal to 0 is a horizontal asymptote. Second case, denominator, numerator has the same power, then y equal to a over b is a horizontal asymptote, a, b being leading coefficient. A is the leading coefficient of numerator, b is the leading coefficient of denominator. Third case, what if numerator has a higher power? There's no horizontal asymptote. So you might say, what does that have to do with our ND behavior? ND behavior, if you look at the power of x, highest power of x on numerator is 1. Highest power of x on denominator is 2. Denominator has a higher power. What does that mean? Your horizontal asymptote will be 0. So horizontal asymptote is 0, and the behavior left and right will approach to 0. Like this question, and the behavior, you look at highest power of x on numerator, which is 1, highest power of x on denominator, which is also 1. So that's power, numerator, denominator are tying. They're same. What do? Coefficient of leading coefficient is 2. Leading coefficient is 3. So it should be 2 over 3. Is horizontal asymptote. What does that have to do with ND behavior? Well, the ND behavior, both ND behavior will be approaching to 2/3. Like this. Same thing. You can approach this analogy for ND behavior. Highest power of x on top is 1. X, highest power of x on denominator is -x, which is 1. First power, so that's second case. Coefficient of x is 4, coefficient of x is -1. So 4 over -1 will give you -4. Okay, so that's this -5. So you can look at this. This one, highest power on numerator 3, highest power on denominator is 3, so they are timed. So 12 over 4, so this is the second case. So 12 over 4 will give you 3. 3 minus 5 will be -2, and that's going to be horizontal asymptote, and that will be the value for ND behavior. So if you like the shortcut, you're welcome to use it. Please do your homework by next Monday. and join me for office hour if you have a further question.